Look at this assembly. A consumer electronics housing attempts to snap into place and violently jams. The paradox here is that this part likely passed every linear and radial dimension on its engineering print. The failure stems from relying on traditional coordinate dimensioning. When an engineer needs to control swept surfaces, aerodynamic contours, or ergonomic shapes, a simple plus or minus tolerance falls short. This chart shows an ambiguous radius tolerance. A callout of R10 plus or minus 1 creates a mathematically poorly defined boundary. The physical surface can wave, flatten, or bulge unpredictably within that limit, resulting in a non-uniform tolerance zone failing to control the actual contour. Modern model-based definition requires exactitude. Instead of ambiguous arcs, the system requires a continuous mathematical boundary that hugs the exact shape generated in the CAD environment. Plus-minus tolerances lack the geometric definition required to constrain modern organic geometry. To bridge the gap between a perfect digital model and a physical object, a specialized GD&T control is required. That control is profile of a line. It is a specific geometric tolerance that targets a single two-dimensional cross-sectional contour of a feature. To use it, we first establish the true profile. Here, a 3D turbine blade is sliced by a two-dimensional plane. That thick, bright vector line tracing the exact perimeter of the slice is the true profile, the ideal geometry derived directly from the CAD model. By default, applying a profile tolerance creates a uniformly disposed or bilateral tolerance zone. Two parallel boundary lines offset equally from that true profile, expanding evenly outward and inward to envelope the shape in a continuous channel. Every point on the physical cross-section must fall within this track. The engineer can alter this using an unequal disposition modifier, denoted by a circle U symbol. This shifts the entire tolerance zone to sit completely on the outside or inside of the true profile line, creating a specific requirement to either add or remove material relative to the nominal shape. By defining a continuous two-dimensional boundary, profile of a line eliminates the ambiguity of coordinate dimensions. It ensures the specific cross-section behaves exactly as the design intended. The power of a profile tolerance scales based on how it is anchored. We start by looking at a feature control frame that references 0 datums. Without datums, profile acts strictly as a form control. This animated diagram shows the two-dimensional tolerance channel freely translating and rotating over a distorted part. The cross-sectional shape must fit within the lines, but its actual location or tilt-in space is completely unrestrained. To lock this floating zone into physical reality, we introduce the Datum Reference Frame, or DRF. We apply primary, secondary, and tertiary datums to the feature control frame in chronological order. Watch as the absolute Cartesian grid appears, and the floating tolerance channel snaps into a rigid position on the grid. By locking the zone to the datum reference frame, the profile of a line is upgraded. It now simultaneously controls the form, the orientation, and the precise location of that two-dimensional slice. The engineer's choice of datums dictates the functional authority and the manufacturing requirements of the profile callout. We can see why this is necessary by comparing it to standard controls. This grid maps straightness, circularity, and flatness to basic cylinders and planes. Straightness only governs a single one-dimensional line element. In contrast, the line profile symbol dynamically traces a highly irregular, asymmetrical two-dimensional curve. Circularity requires a perfect radial slice, but as this curve morphs, the line profile zone adapts to varying radii and inflection points without breaking continuity. Certain functional requirements depend entirely on these non-standard geometries. The aerodynamic lift generated by a specific airfoil cross-section or the precise aesthetic flushness of automotive trim cannot be defined by standard arcs and lines. When standard geometric shapes cannot define the surface and custom contours must be preserved, profile of a line provides the necessary control. In physical production, process variations are inevitable. As we see in this 5-axis CNC mill cutting a curved surface, tool deflection, thermal expansion, and machine vibration cause physical deviations. The profile tolerance zone acts as the definitive net to catch these specific thermal and mechanical form errors before the part leaves the shop floor. To verify these convex contours, inspectors rely on a coordinate measuring machine, or CMM. Here, a ruby stylus is smoothly and rapidly sweeping across a single cross-section of a machined turbine blade. The CMM records this path, generating a point cloud from the physical part. The system digitally overlays this data against the CAD nominal model and calculates the deviation vectors, the small red and green lines, measuring the exact distance between the physical points and the ideal true profile line. The part passes inspection if all calculated point deviations fall safely inside the established parallel boundary lines. Profile of a line closes the manufacturing loop. It converts digital design intent into physical, measurable verification. A common error in industry is incorrectly pointing a line profile symbol at an entire three-dimensional surface, like this curved car roof. Profile of a line evaluates individual cross-sections independently, not the whole surface at once. The inspection requirements are vastly different. Line profile only requires verifying specific two-dimensional slices. Surface profile requires a sweeping laser grid to map and control the entire three-dimensional boundary simultaneously. Another mistake is omitting necessary datums. Without them, a manufacturer can produce parts that possess the correct cross-sectional shape, but are machined in a wrong orientation relative to the rest of the assembly. Conversely, over-tolerancing contours that don't functionally require strict geometric control will increase cycle times and scrap rates without providing additional value. Precise application of line profile prevents the assembly interferences seen earlier while protecting the manufacturing budget from the waste caused by over-tolerancing. Look at these engine turbine fan blades. In aerospace, profile controls are necessary for maintaining the precise aerodynamic efficiency required across these complex curves. In the medical technology sector, parts like this titanium hip replacement rely on profile controls. Its organic, asymmetrical shape must integrate with human anatomy to function as intended. To summarize, profile of a line provides the standardized method for controlling complex two-dimensional cross-sections. Without datums, it controls only form. With datums, it controls form, orientation, and location. Finally, it bridges the gap between digital CAD geometry and the variations of physical production. Mastering individual two-dimensional slices is just the foundation. Next, we scale this logic up to govern the entirety of a part's exterior, transitioning to the control of complete three-dimensional boundaries, profile of a surface.